Good afternoon. Today, I'll be presenting a paper on reliability. Title of the topic is Assessing Long-Term Reliability Through Accelerated Aging Stress Tests on On-Chip Quality and Reliability Platform, a bandgap reference case study. My co-authors are Rahul Sharma and Shiv Gupta, and we represent Intel Foundry, Bangalore. The purpose of this talk is to evaluate and quantify the reliability of the circuit under test. We are trying to do accelerated aging in an analog IP by using the quality and reliability on-chip platform called QROC. Aging analysis is done through accelerated aging stress test methodology condition. We perform a silicon versus simulation sil-to-sim correlation, and we use a bandgap reference circuit BGR as a case study. A quick outline. Why reliability analysis on an analog block? How do we use the QROC test chip and the platform, and what is its overview? What is the accelerated aging stress test methodology, AASTM, defined in this work? What are the results of AASTM on the BGR circuit, and the conclusion? Why aging analysis on an analog block? Our previous research focuses on a lot of design techniques to improve the design parameters. For example, in the BGR circuit, temperature coefficient, TC improvement, and a mitigation technique on PVT variation. Reliability and analysis on the BGR and other blocks needs a little more attention. The output reference voltage Vref degradation of the BGR can cause functional performance failure of the system. Next, in the couple of minutes, I will probably discuss what is the QROC test chip, what is the system. So the quality and reliability on-chip platform called QROC is a platform developed which has a very large test chip die area comprising of 300 plus IOs, and it evaluates various reliability mechanisms. In this, you see, we have test structures for aging, which is called the ring oscillator based test structures, and some analog design IPs. We also have a couple of PLLs and a frequency dividers, which are configured using the scan chains. We have the GPIO along with the clocks, counters, your TDC structures, and the thermal and latch-up test structures. So this is an entire platform that is built internally to do an evaluation on how the quality and reliability of the various IP blocks are correct. The ring oscillator test structure, which is present specifically for the aging, has more than 15K RO instances implemented with different flavors of standard cells and device types. The analog circuit here comprises of the BGR, bandgap reference, and the differential amplifiers. The aging implication of these differential amplifiers can be studied, and that learning can be applied to the various systems. In this particular case, we have the thermal reliability, dielectric breakdown, and also the latch-up structure present to evaluate the various designs. In this figure, we show the actual test board on the right-hand side, which has got the onboard IV measurement, the analog IPs, the heater and test socket structures, the built-in FPGA to perform all the control work, and the power sequencer along with the programmable LDO and other devices. We have a USB device present also to use for external and internal communication systems. So the power information is all present on the south side of the socket, where you see the large capacitors present. Analog IOs are present on the far left for communication. If you see the diagrammatic representation of the blocks present here. So an FPGA is used to do control all the other systems, the USB, LDO bring up, global clock generation, and other circuit interfaces, and the socket and the heater along with the QROC test chip circuit. The accelerated aging test methodology that is being proposed is used to stress the voltage and stress the time to provide a stressed environment for the devices present. The methodology performs is done in 4 steps. step 1. The pre-stress measurement, which prior to performing the stress, a measurement is taken, which is called fresh, or in this particular case, we call it as a time zero measurement. Then the device or the circuit and the tests are now stressed with both a higher voltage and a test time for 1K, 10K and 1 million seconds. The temperature it goes through are -25 to 100, and this physical stress pushes the device into stressed for a very long time, and this may alter the performance of the circuit. As a third step, we perform the post-stress measurement. So in the post-stress measurement, all the parameters present in the time zero measurement are repeated. Finally, the comparison between the time zero and the post-stress measurement is done, and this indicates the robustness of the design and the performance degradation evaluation or measurement of the system. Here we stress the voltage and stress the time in both cases to realize its real-time featuring. In this particular case, let us look at the test case of a BGR circuit. It is a simple classical BGR circuit which has got an amplifier for its in the error amplifier configuration with a negative feedback along with a sense resistor R3 which measures and delivers. We have a couple of capacitors present here which ensure that the gates of M3 and M2 are maintained stable and do not impact the output Vref, and which is governed by the load R3. On the right hand side, we show the two currents, which are the PTAT and CTAT currents, and what is the expectation from the IREF across the voltage and temperature. We expect a nearly flat line with almost no deviation from the standard. The results of the pre-step Vref measurement across the various temperatures and voltages are given below. In this particular measurement, we show the measurement from the input voltage starting from 1 volt all the way to 1.4 volts, which is the stressed voltage, along 4 temperature values: 25, 50, 75 and 100 degrees. In this particular measurement, all the measurements have similar behavior except at 75 degrees, where the value actually increases with voltage rather than reducing. So the overall voltage variation observed is about 7.5 ppm per voltage. Post-stress, when we do the Vref measurement across the various stress time and temperature, we see that as the supply voltage increase starts from 0 to 1.4 on the x-axis, and the normalized Vref voltage from 0 to 1 Vref. As you see the ramp up time starting from 0.2 all the way till 0.8 voltage as an input, you see the ramp up voltage, and there is some deviation from the standard at about 0.4 as an input and as 0.7 as an input. As the voltage stabilizes between 0.8 to 1.4, we see that they are all contained within very much the output value as indicated by the dotted lines between the two, and we see the stress measurement happening at 4 temperatures and 4 time instances: time 0, 1 kiloseconds, 10 kiloseconds and 1 million seconds, or 10 power 6 seconds. So beyond what we observe, beyond the 0.8 voltage input value, the variation in Vref is minimal across the stress time and the various temperatures. Further, when we present the post-stress Vref measurement across the various test times and the temperatures and voltages. In this particular case, we see what is the on the x-axis is all the stress time between 1 kilosecond to 1 million seconds, and on the x-axis we see the normalized voltages, normalized references, and the graph starts from top left is the 25 degrees, to its right is the 50 degrees, bottom left corner is 75 degrees, and to its right is 100 degrees. As you see, the post-stress Vref measurement based on the silicon has got a very stable supplies, and at 0.8 and 0.9 Vref, it degrades with stress time at 50, 75 and 100 degree temperature source. One of the odd numbers that we find is at 0.8 volt at 25 degrees, it actually increases a little. So this is needs a little more analysis to find why this particular anomaly. Otherwise, there is a known degradation slightly across the time and the voltage increase. So in the results, we try and correlate back the silicon with our simulation results. So in this particular thing, we see the 4 steps, where the first step is the design and simulation, where you have the simulation to the model behavior. You predict the device performance and the PVT. As you fabricate the device, silicon fabrication die and die packages go through. And at the measurement, you try and gather the data at various corners and various temperatures. Use the various test cases and test methods to understand. Finally, you correlate the compared measured data to simulation results, analyze and understand the differences, and then correlate it with the simulation model that you have observed. This also incorporates the manufacturing process detailing. So if you look at the second row, we start with the pre-stress simulations, go through a fabrication process, typically perform a measurement, and then plot the results in a post-stress simulation methodology understanding. A quick correlation result. So we have the simulation and the measured results present here. The simulation measure data are present in the various values. The spline covering the silicon measurement in blue shows that it has got very good correlation, and it is present in the center of the silicon results and the simulation range of measurements. So the simulations performed were for the slow, fast, and typical corners with different temperatures. The silicon result closely matches with the typical measurement detail as shown in the figure. About 6.5% difference is observed between simulation and the silicon comparison as with respect to the wide variation that is observed after the system has been stabilized. Not in the ramp place where it is available, where it is wider. It is expected to be wider in the ramp up phase, but as the supply voltage narrows down to 0.8 volt, it stabilizes and it presents a very flat value. In conclusion, this work focuses on the accelerated stress aging analysis of analog blocks like a BGR. The degradation observed was 1% of the Vref under various temperature and stress time conditions after the system stabilizes, and a very strong SIL-to-SIM robustness correlation informs that our particular design is very robust and effective. Thank you. I thank the session chair for giving us the opportunity to present our work remotely, and we appreciate the opportunity. Thank you. On behalf of all my co-authors, Rahul Sharma, Shiv Gupta, this is Dr. G.S. Javed from Intel Foundry, Bangalore. Thank you.